Hello, I'm Tim Holey, and this is session 2 of a 6-session NANA course on open source development using the Julia language. This session is going to focus on the nature of open source development, Julia packages, and then focus most of its time on Git and GitHub. And just as a brief recap, I'm going to assume that there are some things that you already know. Much of the learning in this course actually occurs through the homeworks. There's a link here to the GitHub repository that holds both lectures and homeworks in it. What I'm going to cover today are essentially some of the most foundational things that you need in order to participate as an active citizen in the community of open source developers. So I'm going to even talk a little bit about sort of your expectations you should come to and not come to when you're coming to open source. A little bit about open source licenses. How to ensure that things that you invest in actually were likely to go somewhere, and that it comes down a lot often to recognizing a great package from one that maybe isn't in such good shape. And then I'll talk briefly about the standard structure of Julia packages. I'll talk briefly about package creation, and then the rest of the lecture will really focus mostly on the core Git concepts. And this lecture, again, because I expect most of your learning to occur through doing the homeworks, I'm not going to walk you through click this, type this, etc. This is really much more focused on sort of teaching you concepts, and you'll learn the practicalities from the assignments themselves. So the next assignment, one associated with this session, is the practical use of a wonderful Julia package called package templates that fills out a default repository structure for you with some options that you can set. And then you'll learn how to use Git and GitHub. And you're going to do a lot of that work paired with a partner if you're taking this course at WashU. If you're taking this class remotely, I strongly urge you to try to find a friend to take this along, take at least this session with, and practice as instructed in the homeworks. Okay, and in the final problem, I'm encouraging people to actually become real members of the Julia package development community, and an assignment will be to actually make a submission to a real Julia package to improve its documentation. Okay, so since I am, as part of your assignment, actually sending you out into the world, I think it is actually incumbent on me to make sure that I prepare you appropriately for that. One of the things that's worth acknowledging is that while the world of open source is a great place to get work done, it is also essentially a social media platform, and the hosting sites that provide access to most of the open source code on the internet are also platforms for interacting with other people like yourselves who are developing open source software. And people will get, if you collaborate with people or work in a particular domain, it's very likely that you'll get to know the people involved in that community. And I very much encourage you to keep that in mind. So the most obvious bit of advice is to be nice to the people that you encounter on GitHub, but perhaps a little more specific advice than maybe handy. So, and in particular, software can sometimes get people very passionate, and it can also cause stress if you have some kind of deadline, be it for a course or a grant deadline or a paper you're trying to submit or something else like that. And so sometimes when people, sort of feel stressed, they can do things that they later aren't so thrilled with. And so I think it's just worth sort of making sure that you understand the sort of stage of open source and really what you have a right to expect and what you don't have the right to expect in terms of interactions from other people. So the first thing to always keep in mind is that you aren't a customer, right? You haven't paid anything for the software that you're getting. And so while in the US, at least, we have a phrase that's often used, the customer is always right, you're not a customer. So this is code that's been written by other volunteers. The authors are probably busy people like yourself. They have their own demands and reward structures. They could have kept that code private on their laptops, right? But they decided to put it out there. And if you think that there might be something of value in that, that's great. And that's essentially a gift to you, but it doesn't come with any expectations on their part, right? So if you feel like you've lost a few hours due to bugs in their code, that's more on you than them, simply because they're the one who gave the gift and you are a user of that gift, and that can be great. but it's not their problem if you end up getting yourself into trouble because of what you're using. Okay. And it's also worth keeping, even if you in mind that when you come across packages, you will come across a huge variety of packages. Some of them will be truly sparkling. They will be some of the best software in existence, right? And nothing that no amount of money that you paid could be better than this amazing thing you're getting for free. And others might be a tiny bit of code that someone thought could be useful someday to someone that they just effectively threw over the fence, right? A lot of packages will be somewhere in between that, right? That somebody's put some effort into maybe hoping that it will be useful to other people, but it may be in a variety of stages of sophistication, right? And the one thing to keep in mind is that packages, creating truly great packages takes a lot of different skills. Not only does someone have to be good at writing the code, someone has to be good at writing good documentation that's approachable by newcomers. And if you really need to build something ambitious, it takes not just a single person, but a whole community, right? And indeed, that comes with its own skills in terms of advertising your package, getting the word out about its strengths and weaknesses, about welcoming new people into the fold and getting them incorporated into the team of developers, and making sure that people know, sort of where things are going and how they can contribute and sort of build momentum behind this thing. There's an enormous number of skills that are involved in all of those different areas. And some people may be good at some and not so good at others. And again, that's okay. These are all just volunteers working together. And so, you might be amazed that anything good can come from this. And, the reality is, again, some of the very best software in existence actually have arisen this way. It's quite amazing that it happens. And rather than the current main currency being money, there is money now in open source, right? And a growing number of companies are actually supporting it financially. But the main currencies that drive the open source community forward are both time and passion. And so keep in mind that these are the things that are donated by other people. They love what they're doing and they are investing time to give it to the rest of the world. That's great. You can help them out by donating a little bit of the same thing to them if you really want to become a member of the overall community. So there are several ways that you can actually join this process and help. So one of them is to report bugs. That might sound like you're demanding something of them, and in some cases it can come out that way. But the reality is, I think, is that most developers are very happy to receive good bug reports. If nothing else, it's proof that your package is being used by other people, and that's a very rewarding thing to know, right? But if you've also taken a little bit of time to sort of craft the bug report, then that's something that the developer may find very useful someday for his or her own personal usage, basically. So and sometimes the developers of the package will fix your bug once reported, right? And why might that person do that? Well, a lot of developers know that familiarity with the code does help. If it's my package and I know I could fix it, in 1/10 or 1/100th of the time that it would take you to fix it, maybe I'll just fix it for you. Or I might coach you through fixing it if I think that you look like someone who might, be interested in joining the development team on this project or something, right? And so I'm willing often to invest some time into this, even though I'm not expecting any money in return for that, right? One of the other key things, if you're reporting bugs to a package, issues as they're called on GitHub, for example, is that you should go to the effort to help the developer. So there are a surprising number of cases where the bug report is far too vague to be actionable. I was trying to analyze my data and it didn't work. Can you help me? That's not very much to go on, right? So you should not expect that the developer is going to sort of read your mind about the state of whatever it was that you were doing. The developer can't see what's on your screen, can't see what you're typing, doesn't know what your intentions are. And so what you really need to do is when you do report a bug, you need to prepare essentially a copy pastable set of commands that can regenerate the bug, right? And it should be specifically the bug you're focused on, not some other random bug, because you forgot to specify that this test requires adding a certain package to your environment or whatever, right? So for a person in a fresh, session, should be able to copy paste your code, and reproduce the bug. And if your bug involves lots and lots of different pieces of software always working together, it may take the developer a while to sort of really figure out what the root of the problem is, and maybe even to be convinced that it's a problem in that specific package where you reported the bug, right? And so one way you can really help out is to generate what's sometimes called the minimal working example, or MWE. And what that basically means is that you've distilled the essence of the bug down. You've trimmed away as many unnecessary components as you plausibly can, and come up with a very limited set of things that need to be done in order to reproduce the bug. That's really a wonderful thing that you can do. And that does two really great things, right? So first of all, it shows the developer that you care enough about this issue that you have invested the time into sort of tracing it down to its root. It adds clear evidence that the error is in the package where you're reporting the problem, or very quickly allows you to get at the root of the problem. So it shows interest on your part, shows a willingness to invest some of that time and passion that is the currency of open source. And the other thing that it can do basically is that it can essentially set up a good test for the developer. So when the problem is uncovered in a minimal working example, you can often come pretty close to just copy pasting that working example into the package's test suite. And the advantage of this is that not only does that simple test ensure that your issue gets fixed when the developer submits the fix, but by having this migrate into the test suite, it makes it almost certain that it will continue to work from you henceforth, right? So this is essentially an insurance that you can purchase, so to speak, by submitting a minimal working example, that if it gets incorporated into the package's test suites, you can guarantee that you're going to have this functionality available to you for the foreseeable future. Modulo breaking releases, which change some of the functionality deliberately, but those are usually very sort of publicly announced events and changes in a package. And then finally, keep in mind that even if you've put all of this effort in, it's quite possible that the developer won't fix your bug or implement your feature requests, right? At the end of the day, you have all the code available. You can do the work in principle too, right? And so it's not the unpaid developers, job necessarily to fix these things for you. Again, many developers, if you get great bug reports, will act on them. And if I get 2 bug reports, one of which is going to take me 2 hours of work to trim it down to a minimal working example, and the other one is coming ready-made right at that minimum working example, guess which bug I'm going to fix first, right? I'm going to go with the one where the person has clearly put some effort into it to craft it into a form that's immediately useful to me. So, this is very much a dialogue between developers and users of packages. Now, if you're going to put this kind of effort into packages, one of the things that can be very handy is to know whether your investment is likely to yield returns for you. And so I think there are a couple of things that I would urge you to check. One of them is the license of the package that you're thinking of making this kind of contribution to. And very briefly, license is what declares what you can and can't do with the code, right? So, can you use it in a research project you're working on? Maybe something you're working on might someday become a commercial product. Is that okay? Some software comes with restrictions on whether you can make money from that actual software repository. Are you allowed to share this with others? Can you distribute it to, say, students in a class you're teaching or something like that, right? And are you allowed to, say, modify and distribute those changes? These are all things that should be spelled out by the license about what rights you have as someone who comes and finds this out there on the web and is thinking about using a package or a piece of software. And so roughly these open source licenses come in either sort of, let's say, restrictive forms or so-called permissive forms. For the restrictive license, you need to pay more attention because they're the ones that might constrain what you can do with it. Some of the licenses are commercial or have commercial clauses. So it might be like, say, free to academics, but anybody who's in a for-profit corporation might need to pay in order to use this software. That would be one example. And even though the code is out there, you don't have the right to use it if you aren't satisfying the license terms, right? So that's worth checking. Another category that doesn't involve any monetary transactions, but there are certain licenses that are sometimes called copyleft. That's in distinction to copyright. So this is fully open code, and you can use it and distribute it without any kind of encumbrance. But the moment that you want to start modifying that code, then the key point is that the author of the original package you were using insists that any modifications you're using also that same license applies. So basically, you can't simply by copying a bit of code suddenly start using it on any terms that you dictate. They basically insist that you use the same license terms for anything going forward. Much of the Julia community, at least, is using more permissive licenses, and the most common one, I think, in use is the MIT license. And this is a fairly wide open license. There really are very few restrictions placed on you as a user or developer of the code. And there are a number of others that are fairly similar to that. So these are large and encumbered. I still encourage you to read the license terms for more specifics. These are all named licenses, and the open source initiative vets a certain number of licenses, and when you can, you should use one of these standard licenses. So this shows an example of one of the MIT license from a package that I maintain. It's created called Revise, and this shows you I'll show you on this slide and the next, the entire text of this license. So it's not a long thing that takes forever to learn to read. This basically says that you have permission to do things like use it, copy it, modify it, publish it, distribute it. You can sublicense it. You can even sell this software, right? And that's fine with me. And the only thing that you have to do is meet the following conditions. And one condition is you have to maintain my copyright, this being my package. Whoever's copyright is on the software, right? And one of the things that I should say is that the license file is up on GitHub. It's not something that and I think many developers routinely maintain. Perhaps we should. If you have been contributing a lot to a package, it's perfectly appropriate for you to submit a pull request to add your name to the list of copyright holders because you have made major contributions to it. That's a perfectly fine thing to do. So anyway, so you have to maintain this copyright notice. And then the second thing is a disclaimer of any kind of liability, right? You can't sue me simply because I put this code up for free on the internet. Right. And those are the entire terms of the license. It's not complicated in any way to comply with the terms of the license there. So checking a license is one of two things to consider when you are developing. Like I said, the large majority of Julia packages use MIT license or equivalent. And so I confess, I don't always check the license as carefully as I should, particularly if you're thinking that you might end up being engaged in work that may have commercial potential. You should be very careful and very, very conscientious about checking the terms of the license of all the software you use in developing your product. The other aspect of what is worth doing is because the engagement with the open source community does involve a certain amount of effort on your part. That's the commodity you have to give in exchange for all this amazing stuff you're getting. It's worth it for you to know what is worth and maybe not so likely to be worth the investment of time in it, right? And so I don't want to give you a list and you expect that that things that don't meet these criteria are bad. That's not the right interpretation of what I'm about to say. What I am going to do is give you a number of signs to look for that if you see them, you should be reassured. You should say, this is a very encouraging sign. It's likely to be worth my investment of time into this, right? A new package or one that's in a niche area that doesn't have a lot of usage yet may not have had any time to establish a track record like the one I'm about to show you. And that's okay. It's not a sign that it's going to be bad software. But in software you see that does meet these criteria, you should have confidence. So first of all, just if you hear via whatever mechanisms you use to follow what's going on in your area, if you hear about packages and people have good things to say about it, or it seems like it's really widely used, you can search some of the forums that are useful for Julia packages. If people talk admiringly about a package, that's that's a very good sign about a package. Another thing you can do is that on all of the hosting platforms, you can check for things called stars. So here's an example. Down here, GitHub puts this up at the upper right of each repository, and you can see that there's this list here for stars, and it's saying there's over 1,200 stars associated with this particular repository. And the fact that it's not marked means I haven't personally starred this yet, but I could add my star to it if I'm a grateful user of this package. I strongly encourage you to add stars to packages that you're getting good value out of. Another thing to look for is good documentation of the package. Again, that's typically a sign that the author or authors of that package care and want to support their users and have put in the time, sometimes considerable amount of time, needed to write good documentation about using the package. If you also see that a package has multiple contributors, and again, I'll show you a terrific example of that. This is the so-called data frames package for those of you who may know some Julia packages already. And you can see that this package already has 180 separate people who have made improvements to the package, not just filed bugs. That actually doesn't get you counted as a contributor, as valuable as that can be. But for people who've actually submitted changes, so-called pull requests, to the package to change its actual source code or test suite or documentation or something else, and they have seen those changes get merged by the maintainers of this package. So 180 people from around the world have come together to help create this awesome piece of software. That's, again, a terrific sign about a package. And then the last thing to check is the so-called issues tab, right? So issues is a synonym for bug reports often, right? Or just things that you want to discuss or are concerned about in a package. And so you can open up an issue. And again, this shows you the data frames issue page here. So up here near the top bar, there's a set of sort of major views or so of the repository, one for the code, the issues, so-called pull requests for changes, actions. We'll talk about this one at least a little bit later on in the course, basically. And what you can see here is that this package has over 1,300 issues that have been closed. This means they've been dealt with in some fashion, and about 120 open issues. Now, the absolute count here is not terribly useful. What's more useful is to look to see what kind of responses issues get. And so here there are many, many signs of careful maintenance in this repository right here. So the very first one is you'll notice that a lot of the issues have these little labels attached to them, and that you can access those under the label menu if you want to sort for things by label. This is a sign that someone associated with some level of permissions with this repository has taken the effort to read each issue and categorize it in some way that's meaningful. So that can be an assist to you as a person who might be reporting something, and it's certainly an assist to the developers who work on this package. The next thing that I would certainly notice about this is, and you also notice that many of these come with milestones or other sort of discussion points, and these milestones suggest it's on somebody's agenda now to get this thing addressed in some fashion. The next thing to look at is these little quote bubbles here with a number after them that indicates the number of follow-up posts that have been made to each one of these issues. And what you can see is there's been vigorous discussion and just simply response to someone filing a new issue. And if you look at the day clock, if you click on an issue and open it up, you'll typically see with data frames that the posted issues typically get a response quite quickly. Sometimes it doesn't mean that a fix is coming immediately. There might actually need to be a fair amount of discussion and head scratching and thinking about what's the best way to address an issue. So some of these discussions can go on and for many posts back and forth. But what you can see is that your anything that you are likely to say in this package is unlikely to languish. You might say, well, there's a couple that don't have a response. And yes, but I also happen to know the people who posted them are some of the developers of this package, right? And so they don't necessarily need to respond to their own issues, right? So they're just posting this essentially as a to-do list item for themselves, but ones that are being reported by outside users or people who are not as central to the package in data frames, get a fast response. And finally, you can see that some of these issues have this little symbol here. This is the kind of universal symbol for a so-called pull request. This means that there's a fix already queued up to close this issue here. And you can see that quite a lot of them, have pull requests that are already queued. They haven't been merged yet, or this issue would likely be closed. But for whatever they may be waiting for feedback from someone. Does this fix your problem? And it's incumbent on you as the reporter at that point to test it out and say, yes, this is perfect. It fixes my use case exactly, or whatever, right? Many times they'll know that if you've supplied them with an MWE, but in cases where that's harder to do, they may require verification from you that this addresses the issue you reported. So anyway, tons and tons of terrific signs of just platinum level maintenance in this package. You would be lucky, I think, in many pieces of software that you pay big bucks for to get the level of service that you get in a repository like dataframes.jl. Okay. So let's move on. So having now know some tricks for how you vet useful packages and figure out which ones are maybe worth your time investing in, and others where it may be a bit more of a gamble. Now it's time to start talking a little bit about how you actually read the details inside of a package. And so in this course, you're going to create several packages. I'm showing you a very simple, almost sort of skeleton state of a package right now. And this is one that's created by this repository I'll mention a bit called packagetemplates.jl. And it lets you configure a number of options. And there are sort of 4 key directories that I want to, folders that I want to call your attention to. The first is this .github workflows directory. This is part of the sort of testing apparatus and other sort of maintenance assists that package template sets up for you. We won't go into those at all today. But they'll be addressed in future sessions of these lectures. The next one is this docs directory, which contains all of these things here. It includes this source folder, and this is where the documentation for the package lives or may someday live. This happens to be a blank package basically, and so it doesn't really have any documentation. But if I wanted to write documentation, the first thing I would do is start editing this markdown file index.md. This make is for building the documentation. You may notice a project.toml file, which you hopefully know from having done the previous homework. That's a different project toml file than the one for the package, which is the one I've got highlighted down here. This is the one needed to build the documentation, whereas this is the one that's needed to define the package. So don't get these 2 project files confused with one another. And then the 2 probably most important directories, the source directory, which contains the source code for your package, and the test directory, which contains the test suite for your package, right? So these are really where the sort of main software content of your package resides, basically. There's the important license file, which I mentioned briefly, which dictates what users of the software and contributors to the software can and can't do. And then this project file, this really defines both the name of the package. You'll see all Julia packages come with this UUID, and you think of that essentially just as a random number. And what it is, it's a unique identifier for your package. And the reason that's necessary more so than just your name is that oftentimes many people will gravitate towards similar names. You may have, in principle, if a package for dealing with prime numbers might be called primes.jl. Well, if 2 people create packages called primes.jl, then there's a name collision. And what the UUID does is uniquely resolve any kinds of name collisions like that. So the Julia package manager is fantastic. And it's, I think, one of the very few package managers out there which can, in fact, allow you to exploit 2 or more packages with the same name. Obviously, you don't want to deliberately go there if you don't have to, but the UUID does allow you to resolve such issues, basically. And then there are a few other things. We'll talk more about some of these other things when we talk about package compatibility and dependencies and things like that. Okay, so In this class, again, I'll have you creating new packages. You may see online documentation about how to do this. And roughly speaking, there are two commonly used strategies. A low-level approach is to use the package standard library itself, a function called generate. In this course, I recommend that for almost all cases you would use, and I think all cases in this course, you should really use this package templates.jl package. It's a fantastic package. It sets up a lot of stuff for you, not just that overall standard structure, which package.generate does too, but it initializes a lot of these sort of test harnesses and other things like that that can just take some of the administrative burden off your plate. Okay, so again, I'm not going to walk you through how you use this. You're going to learn it on the homework. The main topic that I want to cover today is the topic of version control. And this is an utterly crucial issue when it comes to software. And again, I'm not going to teach you how you use the tools. You'll learn that in the homework, but I do want to teach you the underlying concepts. And so to motivate this issue, if you've really not even had to deal with this yet in your software development, you may have some familiarity with this if you've shared documents with collaborators. So for example, if you're writing a text document of some kind, you might send around by email a draft of that text document to your collaborators and say, hey, here's my draft, of this report we have to write, make any comments or edits in this and mail it back to me, right? And, this is a workable strategy, but especially if you have more than one other person that you're collaborating with, this does fairly quickly get complicated, right? So if you have multiple people you're sending it to, they don't in real time see what each other's work is, because each person gets their own copy of the file, edit it locally on their machine and email it back to you. So you may have 5 people all making basically the same comment or making changes that address the same underlying issue, but in 5 different directions. And it's a lot of redundant work because they don't have a chance to sort of see what's going on as they work their way through the document. Another issue is that you may have to merge the changes together from these multiple responses that you get into a new one. And there's even annoying things like, if I receive a version 1 of a document and make edits, is it now version 2, or do I append my initials or something else to the file name? So everything from, how do you endow the files with meaning in terms of where they are and the history of working on this project? Where did you start from? Where have you brought it to at this point? None of these things are handled particularly well by this kind of workflow. And so you also then hopefully may be familiar with one of the really nice ways of solving this problem. If you've ever used, for instance, Google Docs or similar services, you may be familiar with a workflow that's really designed to solve a lot of these problems, right? So in this case, there's an online server, you turn on sharing for the document, and the document exists online, right? And so when you open up that sharing, then what that means is that anyone working on it, and multiple people can even work on it simultaneously in real time, you see the changes as they happen. And that, of course, ensures that the changes are essentially the union of all active ongoing changes. And this preserves the notion of a single master document. You don't have to do nearly so much to merge all of the different commentary and suggested changes together if you're going this way. So this really solves a lot of the workflow problems with email. It has a major con to it, and that is that in a certain sense you can't work on it at all if you're not connected to the internet. So if you're in an airplane and you're not buying the Wi-Fi, or on a bus or something like that, you're not doing that. Now there are steps you can take to ensure that you check out sort of get a local copy of it, and you can edit it locally and then sort of resubmit. But that pretty much breaks the model, right? At that point, somebody may have to merge some of your changes in manually again, possibly, especially if things have gone off in a different direction at the time. So you might imagine, therefore, given these descriptions, that the right way to solve this in the software world is to just go with this centralized version control, right? Make everybody be connected to the internet and all the changes happen up there. But that would actually be a disaster for software. And what software has done is standardize on a model that in some ways is closer to the email way of working, but handles the merging and bringing the differences together in a way that involves vastly less manual effort. So Why is that? Why is this? This is often called distributed version control. It's distributed means simply that many different people around the world can be working on something simultaneously, and yet you can make sense of all of their changes and bring them all back into a common whole, which is amazing. And the most widely used tool for doing this is Git. So why is the centralized version control model not adopted for software? Well, the most important reason is the following. Let's say that I'm working on a widely used piece of software and I'm interested in tackling a really ambitious, difficult to solve problem. It might take me 2 weeks of essentially continuous work on this in order to implement this new feature or fix to a deep problem or something like that, right? If every change that I made in the progress along the way towards modifying the source code ended up immediately propagating to everyone around the world, I would almost be guaranteed to leave the software in a broken state, right? I'm partway through editing, and all of a sudden, anybody who tries to jump in at the process has this completely busted piece of software. So, with a text document, if you're writing it, if you make a typo in line 3 of the file, it doesn't prevent people from reading and from making changes to line 200, right? But in software, if I make a typo in part of the software, it can bring the whole system down and nobody can use it. And so that's really the fundamental reason why this sort of centralized server version control, immediately propagate all changes to everyone model just simply doesn't work for software. So you need a way for developers to work on something privately for a period of time, but then you need a mechanism to bring their changes back in. And so Git, this most widely used solution for distributed version control, has a number of features, and it's worth emphasizing what those features are. So first, one that may be surprising is there is officially no single sort of master version of the state of the repository, right? So any copy of it essentially could be just as official as any other copy. Now, in practice, it often turns out that there is a kind of a gold standard version of the software that everybody turns to. But that's really more of a social construct, not a technical one. If so-and-so is the original creator of the piece of software, shared it up on GitHub, and in that person's personal GitHub account, and lots of people band together to keep working on it, it's still that version hosted in that person's repository account. It is essentially the official version that we all work from. But if that person abandons the code at a certain point, stops being responsive to requests, maybe because they've gotten busy or changed jobs or whatever, and isn't interested in seeing the project go forward anymore, we're not stuck, right? We can all decide as a group, okay, this new copy of it is going to become the official one, and let's make that, in some senses, where we all put our efforts. And so there's no technical barrier to switching where you send your changes to in Git. It's very much important, as described, that the different copies don't automatically sync. It requires manual effort to trigger syncing between two versions of the same software. And the merging is based on disparate changes that have to be based on shared history. Okay. Now, wrapping your head around these things is much more complicated than these sort of simple descriptions might seem. I personally think it's useful to have a couple of analogies in your head. And my favorite analogy for how Git works is actually a bit like biological evolution. It's not a perfect analogy, but it has enough strengths that it's worth thinking about. And I'll point out where the weaknesses are. So biological evolution, I would say, is actually a reasonably good mental model to hold in your head as you start getting comfortable with Git. So, for example, in species, just like Git repositories, there is no master copy, right? Each individual is essentially potentially equivalent as a noteworthy example of the species, basically, right? There is no official version of the species, right? In biological evolution, there's a process of bringing sets of changes together, and that's mating, of course, right? And the production of offspring from that. So that combines the mutations from two parent organisms. And that's a lot like merging in Git. with some different important differences. And the final thing, and this is really where things are super, super important, is that there isn't the ability to synchronize these repositories to have a productive mating that results in offspring within a species, unless they have shared history, meaning that foundation of sequence homology that comes from their common descent. 99.9% of all of their bases in their genome are essentially identical. The changes are just a sort of a small difference, and it's that foundation of sequence homology that allows mating to occur in biology. It's that foundation of shared history that allows seamless merging in Git-based projects. Okay. So, this model is not perfect by any means. So in software, there's much more of a social drive to eventually unify everything into a single thing. There's no particular drive for a species to be a single thing, right? They're essentially just a collection of equivalent individuals, right? Also, unlike biological evolution and reproduction, when you make a merge of two Git branches, as they're called, the changes are merged exhaustively, not just randomly as they are in homologous recombination, right? Meiotic recombination. And then the final pretty obvious difference is there's no analog of the sexes, right? So any two individuals can merge if they have shared history, okay? So this works really well. It turns out Git works really, really well for code, right? So it has the advantage that you can develop your feature without interference from unrelated changes that may be happening all over the world. And the bigger a project becomes, the more contributors there are to it, the more important this becomes. And then you can combine your changes only when they're ready, right? So that's great. And then it does have downsides. Occasionally, from this distributed model, you do get conflicts sometimes, and those conflicts require manual merge. The nice thing about Git is that in places where you wouldn't think there should be a conflict, there generally isn't one, right? And it's just those places where you as a human would be likely to say, okay, yeah, these two people took this in two different directions, and if we can't merge both sets of changes, we have to figure out some way to either pick one or get them together in some fashion, right? And so, and the real strength of Git over some previous versions is that it gets the simple stuff right? It doesn't require any real effort on your part, and it's only the hard stuff where there isn't an easy way to address the question that requires your manual attention. And as trivial as that may sound, it was not a common feature prior to the emergence of really good distributed version control systems. And so, one way that may help bring to fore what can be a little bit complicated about doing this kind of process is to imagine how a merge might work. So let's say that I have two versions of the code. I'm going to call it A and B. In Git lingo, these might be two different branches of the code, right? And there are 3 lines of source code here, right? And the first and third are the same between the two branches, but the second ones differ, right? And so you might say, okay, great, here's a difference between the code, let's merge them. Well, which of these should you pick? Which is the authoritative one? Is it A or is it B? Well, if this is all you have, you don't know, right? You don't know really anything about why they're different, and you don't know anything about which of these is newer, if there is one, et cetera, right? And so this is where the history really comes into play, right? It essentially endows modifications with the directionality. So typically, what you would hope would happen is that say B would maybe start from A, or A might start from B, or they might start from a common ancestor, right? Before other people started making interesting changes, right? And if, let's say, they both started out being Y equals 2, and then this version here, B, branch B, change it to Y equals 3, it seems pretty clear this is an update to the code. This is a new thing that we now need in our code. And so when you make the merge, it's this version then that will take precedence, because it's the change that you have requested be merged into the overall source code, right? And so this is where that shared history is so crucial, to keep that shared history in sync, in the package and among your developer community, which may be scattered all over the globe. Okay. So let's talk. So all of this applies to any distributed version control system really, but Git is the only one we're going to use in this course, and that's because it has really become the dominant version control system for software. The Git logo is worth noting that this is a symbol symbolizing this process of branching, of starting two separate sets of changes from a common ancestor, and that just reminds you, right, that this is a very crucial thing to keep in mind about how Git works. You can install Git on all the machines that you use, and definitely all the machines that you're planning on sharing software across. As I'll describe, Git you can use completely locally. It's independent actually of hosting services like GitHub. So we'll get to those later. I first just want to describe Git in and of itself to you, and you can run Git either just on your own machine. I use that sometimes just to simply take snapshots periodically of a project I'm working on, even if I never intend to share it with anybody else. But it's especially handy to you if you have several different machines you use and you want to keep your code in sync, even if, again, you never publish that source code. Right, so that's a really key issue. So the hosting services like GitHub, there are others that many people love a lot, GitLab and Bitbucket. All of these are essentially ways of getting your code up onto the web and into the hands of additional pool of users. But Git is useful with or without this kind of hosting service. Okay, so I want to describe the core Git concepts to you, and they're really, in my mind, three main concepts that you really need to get your head wrapped around. And the first one is this so-called branch and merge workflow, right? And so the idea basically is here, if let's say a repository starts out in this state and it has a single what's called branch, here is called main. This is the default chosen on GitHub. It's historically Git chose master as the name for the default branch. You may see repositories with either one of these or even other names, but there should be essentially one branch that's sort of marked as the primary branch for this repository. What each one of these circles here represents something called a commit. So you should think about a commit as a snapshot of the state of your code. And I'll talk a lot more about how you decide what goes into one of these snapshots. But roughly speaking, you expect these snapshots to occur at moments where the code is in maybe more complete, or let's say just better shape. For example, if I were editing a file, I wouldn't tend to have an open parenthesis and then make a commit if I hadn't closed the parenthesis as well, right? That is not the kind of thing. If I started a function definition but hadn't yet finished the function definition, I would wait until I'd fleshed out that function definition before I made a commit, for example, right? So these represent sort of moments in time at which the package may not necessarily be working, especially on main. It's kind of nice if it works at every single commit. But that may not be true at intermediate stages on branches. And so these commits are sort of moments where you've taken a snapshot of the state of the code and you've effectively archived it. It's worth noting that Git allows you to check out the state of the source code at any commit. And that can be whether it's on a particular branch, and you might check it out by branch name, or a particular commit. If you're interested in going back in history and seeing what things were like at a certain point, you can check out the repository in a particular state. And the beautiful thing about Git is that when you've selected a commit and checked it out, or selected a branch and checked it out, your active code that Julia will use goes full bore towards that state. So you may rewind history by 6 months in a few keystrokes, right? And see what things were like back then, and then go right back forward to the modern time in another couple of keystrokes. Or you may test some changes that you or someone else is working on and then go right back to the main one. This is a wonderful, wonderful workflow. If you have a package that you're actively using, but you have an ambitious set of changes you want to make, like you want to make this little branch right here, these are going to take you several commits because this is hard stuff and it takes some good thinking time. But meanwhile, you may need to be able to use your package and deliver some results to it for someone. You can toggle back and forth between this ambitious branch where you're rewriting things and your main branch where things are just working. You may quickly add a couple of new features to that branch. Someone else may, meanwhile, while this main branch is ongoing and you're working on your difficult feature, someone else somewhere else may report a bug on it. And either that person or you might fix this. And this allows you to check out another branch and then make some changes to the code, get those merged back in. And what you notice is that you can branch off at any time you want and merge back in at any time you want. And as long as the different branches are not doing different things that started at overlapping times where they were not both merged or both absent, then of course, if when that happens, bad things can happen. You can get merge conflicts, but anything that doesn't overlap in time with the same set of changes incorporates the full sequence of history that was merged to main. And so, and if what's going on in this branch is different from what's going on in this branch, there's no conflict, and both sets of changes can be merged hassle-free whenever the moment to have them merged arrives. So this lets you both keep your code running, do ambitious things that make it a substantially better package, and commit quick fixes that fix critical bugs and get them out to your user base without needing to wait until something that's much on a longer time horizon gets to the finish line, basically. So this overall branching and merging workflow is the nicest thing about Git that it enables. It is what allows a repository to receive contributions from tens, hundreds, thousands of people, and is really the main part of the sort of success of something like Git. It's important to know on a finer scale when you're actually working on the repository, keep in mind that there are sort of different, what you see is essentially a particular sort of snapshot of the code. So your entire history of the repository is stored in a hidden directory, .git, and this stores the entire sequence of changes that have been committed to the overall package. And so this is what makes it a Git repository, right? Is the existence of this .git directory, which contains the contents that Git expects to find there, right? The code in your working directory, this is what Julia will use. This is what Julia will run. It will define the source code of the package. It will define the documentation of the package. It will define the tests of the package, right? So whatever is in your actively working directory is what you personally see right now whenever you use this package. Now, your working directory might be a direct snapshot of a particular commit that's in the Git history, but you also then might start making changes that you have not yet committed. So your working directory may contain a starting point at a particular commit, but then a set of local modifications, none of which have become part of the Git history yet. When it comes time for you to make another commit, it's actually a two-step process. The first step is to do what's called staging the fixes, right? And what this basically means is essentially transferring things from work in progress, I'm actively editing the files, into this is basically ready to commit. And it's as simple in VS Code as a single click of a button in many cases, but the existence of this staging area lets you be more refined. You may have edits to 3 or 4 files, but you may only be ready to commit those changes to 2 or 3 of them, and they may actually function as a unit, whereas the other thing is something you're still kind of working on or something like that, right? So it also allows you to choose what just simply goes into the repository. So for example, let's say I'm debugging something and I find it convenient to have during debugging it to generate just a dump of output or something to a text file or something like that, right? I don't want that text file to become a part of my actual package, right? This is just for my local use as a developer as I try to figure out the bugs in this package. And so I don't want to stage that new file, right? That's a file I don't want to make part of the package, and so I leave it out of the staging area. So the staging area is essentially where you queue up the full set of changes that you want to be part of the next commit. Once all those are ready and ready to go, then you make the commit. And this is the moment of like pressing the button on the camera You snapped a picture, you've taken a picture of the current state of the repository as it is in the staging area effectively, and this transfers it into the history of the project. And if you transfer it into the main repository, now it's, or main branch, it's now part of your local copy of the official history of this package. If you're making changes, I strongly recommend that you use a branch, because the branch is what is essentially there for you for in progress kind of stuff, that then at some later point should be sort of more officially merged as a unit into the main branch of your repository. Okay, and again, you can switch between different branches. That updates what appears in your working directory. It doesn't change the history that's stored in the Git directory. The final sort of core Git concept that I think you really have to know about is the concept of remotes. And so this is really where you can use, this is key to the ability to use Git with GitHub, but it's also key for you for sharing code among several machines you control. And a good example from my own personal history, I had 3 machines that I used frequently. I wrote a lot of code on my laptop. I had a lot of the sort of more serious number crunching my laptop wasn't really up for, and so I had an analysis workstation. And then I also had a data acquisition computer where I was actually collecting the raw data from my experiments, right? But it was, you know, these had maybe a few differences in terms of what code was there, but a ton of shared infrastructure was, I wanted to be present on all of those machines. And in the early days, before I learned how to use version control, I would just try to copy files. So if I made a bug fix on my acquisition computer in the middle of an experiment, I tried to remember to propagate that fix to other machines, but it pretty much was a disaster, right? And what Git allows you to do is to start from that point of common history. You can easily ask, oh, what changes do I have on this machine? Oh, whoops, I forgot about that change. You know, I haven't shared that with my other machines yet. And so you see that you have these unstaged, unmerged commit, changes to the repository. You stage them, you merge them into a branch or the main thing, and then you want to share them with other machines. And this is where this concept of remotes come from. So to every given computer that you may actively be working on at the moment, that machine is the local repository. But then you can define within the Git repository some additional remotes, and remotes is just Git's term for machines elsewhere effectively. And so I might define one remote for the analysis workstation and another remote for the acquisition computer. And what this lets me do is sort of send or receive code from each, with my laptop. And sort of the standard terminology for Git is that a push is when you're sending code from a machine you're currently working on to another machine. A pull is when you receive code, you ask that other machine, please send me this bit of code that I'm asking, or this branch I'm asking to pull down from you to me. And then the final one is a clone, which is a lot like a pull. It's just what you use when you're making the initial copy of a remote repository. So these have different needs associated with them. If you're making a push, you obviously need to be able to read the state of the code on your local machine, but then you need to have write access to the remote, or the remote won't let you shove that code upon it, right? Conversely, if you're making a pull, you need to be able to read the state of the repository on the remote computer and then write whatever updates and changes are present to the machine you're currently on. So you need write access to the local in that case, right? For a clone, you need read access from the remote and write access on the local. So it's basically, again, the same thing as a pull, okay? So this ability to define remotes, you can give them names, and that lets you share code very easily across machines. You can do this locally, just on a set of machines that you control. But the very same concepts apply when you want to put your code up on the web for everyone to gain access to. But for that, unless you happen to run a high availability web server, your best bet is to use some kind of hosting service. And so for that, in this course, we'll be using GitHub. But again, there are several other much loved competitors to GitHub. When you start thinking, though, about using a hosting service, there's one additional set of ideas that you need to know about, and that's the concept of a fork. So forks solve an important problem. Let's say that you want to start contributing to a package that you find up on GitHub, You might clone it down to your local machine. That's fine. GitHub lets you read the code that's up there. It's available for anyone to read. And then since you can read it, you can pull it down to clone it, pull it down to your local machine and write a copy of it down on your local laptop. You can make whatever changes you want, but now you get to a point where you want to submit your changes back to the upstream, right? And then you have a problem. This is your first time ever. You've never even introduced yourself to the maintainers of this package. They have no idea who you are, and they're not going to let you just write files and make changes in their repository, right? And so you don't have any permission to push code from your local machine, right? Well, you might say, okay, how about this? Can I ask them to pull the code from my laptop? And that might be good, but that also introduces a few problems. You have to give them privilege to access the code on your laptop, and they might do that from a variety of machines. They may not be going through GitHub. They may be doing it from their work machine. You don't know what their work machine looks like, so you're not going to grant random access to some stranger on the internet, to your local laptop. And what if you pack up for the day and go home at right around the time when they're ready to review your changes and see if they make sense and maybe merge them, right? Suddenly your code is no longer online and they're sort of sunk. There's nothing they can do, right? So this would be a really not very effective workflow. And so what you instead do is you do something called forking the upstream, right? In that case, what that means is that still on GitHub, you make a copy of the code. So effectively, you're cloning it from the upstream, not down to your local machine, but you're cloning it to your own personal account up on GitHub. How does that solve problems? Well, so if you clone your copy of the project from GitHub, you can bring it down, you can make changes, but when it comes time to submit your changes, you have write access to code that's in your personal account. You just don't have write access to code that's in somebody else's account. So you can push your changes from your local desktop, local laptop up to GitHub this way. It's now sitting in your fork of the upstream repository, but it's not sitting in the upstream fork. Now you submit that pull request, the one that we thought about submitting from your local laptop before, but instead of pulling the code from your laptop, it's going to pull it from your fork of the repository up on GitHub. And this solves a lot of those problems, right? This is now public, just as public as this is. Anyone can see it, so the developers can see what your changes are, and they can incorporate them and merge them at their convenience. This is high availability. This is always online, and so there aren't the other, sort of restrictions on when the machine is available because it's solved by the hosting provider. And so this workflow is the standard one that you should imagine using. At the same time, you can have multiple remotes. You can add the upstream as its own remote, or if you clone directly from here and later realize you want to contribute to the package, you can define a remote for your fork up on GitHub. All of those are possibilities, okay? So those are the core concepts of Git and GitHub. And I hope with them that once you then start digging into the practical details, which you're going to do on your own, I'm not walking you through that. Hopefully this will really come home to you and help you develop a mental model for what's going on with all this kind of stuff. The last thing that I do want to say, and I'm not going to go over it in detail, but I do want to acknowledge the fact that Git is history-based, that while it's history-based, you can actually rewrite history, and Git provides you with some tools to do that. And in fact, these tools are very nice. If you use Git for a long time, I strongly recommend that you learn how to do things like rebases, right? It's a very, very useful technique, but it's a very dangerous technique also, and you should not tackle it until you have a clear understanding of what's going on behind the scenes with Git, a good mental model of what Git's doing, and some degree of comfort in using Git. And the reason, first of all, is it's a little bit complicated until you have that confidence with Git. The second thing is you can actually actively do damage this way, right? And the reason you can do damage is, keep in mind, the ability to make merges in Git is based on history. So if you go rewriting history, you may be cutting off your ability to merge two branches together, right? So don't do this without good reasons to do it. And one general tip, there's no such thing as never, but almost never should you ever even remotely consider any form of rewriting history on a branch like main, right? The reason why is main is the branch that everyone in practice will probably begin from with their changes. And so if your version of the history of Maine starts differing from the version of history of Maine in other people's accounts, because you've rewritten it, you've suddenly erected massive, massive barriers to collaborating with other people. So basically, treat Maine as inviolable, right? Once something gets on Maine, it is part of your history and you don't go changing that. You can change history on branches that haven't, they're intended to eventually merge to Maine, but have not yet merged to Maine. You should never effectively, almost never, even remotely consider changing the history of a branch like Maine. Okay. As long as you know that, once you start feeling comfortable with Git, these are terrific tools to learn how to use, and I strongly recommend that you do so. Okay, so brief summary. Git and hosting services like GitHub are really what fuel open source in many ways, and they enable worldwide collaboration. These are social media platforms, the hosting services are, so be very respectful and you'll earn the respect of other people. There are really not that many core concepts that you have to know, but it's very complicated and confusing until you wrap your head around these core concepts. So remember that changes get staged and committed. A commit is a key moment in the life of a branch. Branches get pushed, pulled, and then merged together to bring these separate changes based on their history together. One other tip when you read, if you read online Git documentation, which is a great thing to do, one of the things to keep in mind is that Julia has streamlined some uses of this. And so for instance, I like when I'm working on a package, instead of doing the more manual clones, which you'll see described as sort of a generic way to clone a repository, Julia's own package.develop or package.dev for short, if you're working in package mode, allows you to clone a repository, and it just sets up a couple of nice, nice things for you. Also makes it available to your session, etc. So I often use that. So using the Julia tools as essentially a front end for some of these Git concepts is not a bad thing. So again, you're going to go over all the practicalities on your homework just to sort of remind you what that looks like. You and a partner will both create sort of compatible, sort of almost mirror symmetric repositories with different names. You'll both submit pull requests to both your own packages and each other's packages. You'll learn how to review a pull request. You'll learn how to respond to review comments. You'll merge your partner's contributions to your package. Then that will set up a conflict in Git, and the homework will walk you through how you manage that conflict and bring those two independent sets of conflicting changes now together. So this is a real world exercise in what it's like to use Git. Doesn't really sort of shy away too much from some of the harder steps while still keeping things, I think, pretty simple. And then the final problem of the homework will be to submit a so-called module doc string. It's an improvement to the documentation of an established package. And hopefully after you've done this, you'll all be credentialed Julia package developers at that point. Okay, that's all I wanted to share. Thank you for your attention, and I'll see you in the next session.